Good morning, students. I have left my previous topic on the same reaction. So here I was talking about nucleophilic substitution reaction. Here, this is the nucleophile and this is the alkyl halide. Now here, if I talk about the halogen, you know that halogens are also electronegative. This bond is polar. That is why they are carrying delta negative charge. Now nucleophile is also having negative charge. If this species will be attacking from here, then it will be facing repulsions. So it will be attacking from this side. And if it is a strong nucleophile, then it can displace this weak nucleophile. Here it is also nucleophile. I told you the properties of nucleophile. Negatively charged species, here it is also nucleophile. So when a strong nucleophile displaces the weak nucleophile, such type of reactions are called nucleophilic substitution reactions. So here your nucleophile is attacking here and this is leaving. Now here, when this nucleophile is getting replaced, obviously it will be displacing only when it will be weak. So this will be working when it will be a weak nucleophile. It will be known by the name leaving group. This will be known by the name leaving group. And the product formed will be this one. The strong nucleophile will be attached to the alkyl group. Now in this category of reactions, I'm having few reactions which I want to discuss with you. The very first category of nucleophilic substitution reaction is alkyl halide when reacted with aqueous KOH. Now in this aqueous KOH, what is the nucleophile? OH minus. OH minus is a strong nucleophile and it will be displacing your X. X, that is halogen. If you see aqueous, remember this thing in mind. If it is aqueous QH, then only this kind of substitution will be taking place. If in place of aqueous it will be alcoholic QH, then it will not take place like this. Then if you remember about the beta elimination reactions, which we have done in the 11th class. So remember this thing, aqueous QH and alcoholic QH makes a lot of difference in the reaction. So when QH is taken in the aqueous medium, here OH negative works like a nucleophile, and being a strong nucleophile, it will be displacing your X, resulting in the formation of the respective alcohol as shown in the equation. So when your alkyl halide is made to react with aqueous QH, the displacement will result in the formation of the alcohol, and the X or the alkyl or the halogen, respective halogen, will be eliminated in the form of leaving group. In the same category of reaction, if you look at this reaction, alkyl halide when reacted with sodium alkoxide, here this alkoxide is working like a nucleophile. Now this alkoxide, being a strong nucleophile, will be displacing X. Alkoxide is OR dash. Here alkoxide is indicated by OR dash. Now this is a strong nucleophile and this will be displacing your X, resulting in the formation of ROR dash. What is this? This is ether. This is your ether. We have already done the nomenclature of ether. So this is your ether. And your X will be eliminated in the form of leaving group. Okay. This reaction is also known as Williamson's synthesis, which is there in the next chapter, alcohols, phenols and ethers. So the same reaction you will get in the beginning of the ethers, preparation of ethers. We'll discuss about this reaction. So it is again a nucleophilic substitution reaction. So here again I have taken the example of this only, that is sodium ethoxide. Here I have taken. So this ethoxide, it is a nucleophile which will be going to displace this bromide, and bromide will be here as work like a leaving group, and your methoxyethane will be formed, which is an ether. So this is a nucleophilic substitution reaction. Again, in the same category of reaction, if I react ethyl bromide with silver oxide, if I heat this ethyl bromide with silver oxide, again same, what will happen? Your EGBr will be eliminated and ether will be formed. Ether will be formed. So this is again the same category of reaction. We can make ether by this method also. This is an easy method of making ether. The detailed preparation of ether we will be doing in the next chapter, but being a part of nucleophilic substitution reaction, I have discussed the same here. Now I'm switching to the next category, and that is a very important topic. In the next category of nucleophilic reactions, I'm having alkyl halide reacted with KCN in the alcoholic medium. When you heat alkyl halide with potassium cyanide in the alcoholic medium, if you see, your alkyl alkane nitrile, or you can say alkyl cyanide, will be formed here. Cn negative, again it is a strong nucleophile, will be going to displace your weak nucleophile, that is X. So again it is a nucleophilic substitution reaction. I have taken example of methyl iodide. Again I have taken the same, reflected the same thing, that Cn is displacing the weak nucleophile, that is I minus. Now if I take, in place of potassium cyanide, I have taken silver cyanide. Rx, alkyl halide. Potassium is a metal, silver is a metal. Potassium cyanide I have taken in the alcoholic medium. It was resulting in the formation of alkane nitrile or alkyl cyanide. But when I am taking silver cyanide in the same ethanolic solution, in place of alkyl cyanide, I am getting alkyl isocyanide. If you see RNC here, it is alkyl isocyanide. Now, now the question arises, why this change is there? If you are taking KCN, we are getting alkyl cyanide. If you're taking EGCN, we are getting isocyanide. Now, why this is happening? And this is a question in NCRT also. I've taken one example also reflecting the same thing, methyl isocyanide preparation. Now, what is the reason of being there? The whole concept is hidden in the case, in this your nucleophile cyanide. Cyanide is basically known as ambident nucleophile. Now, what is this ambident nucleophile? If you see, I have drawn resonating structure of cyanide in this. In these resonating structures, if you see, cyanide is capable of giving electrons from the carbon side as well as from the nitrogen side. Means it is having the tendency to get itself attached to a respective molecule from carbon as well as from nitrogen, because it is having the capability to work like a nucleophile from both the ends, because it is having electrons, one lone pair of electron which is reflected on carbon, and there are excess electrons on the nitrogen. So it is having the tendency to get itself attached either from the carbon or from the nitrogen. So any nucleophile which is having the tendency to get itself attached from more than one sides, that is called ambident nucleophile, and your cyanide is one of them. Now here I have given one more example of ambident nucleophile, that is nitro. If nitro is getting attached from nitrogen, NO2, here nitrogen, and it is having the tendency to get itself attached from oxygen also. Oxygen is also having negative charge, excess of electrons. So this again is an ambident nucleophile. Now how this ambident nucleophiles affects the reaction? In this case, the situation is happening because of this own property of ambident nucleophile. So for discussing these, the exceptional reaction which I talked about in the beginning, if you take NaCN or KCN in the first reaction which we did here, alkyl halide reacted with KCN, alcoholic KCN. If you take KCN or NaCN, the both the KCN and NaCN, they are having ionic bonding, and being ionic in nature, the cyanide which is there, it is having the capability to attach itself, because in an ionic compound, K positive will get separated and Cn negative will get separated. Now this Cn negative is having the tendency to get itself attached to either with the carbon or from the nitrogen. Now the question arises, why it is getting attached only from carbon? Because when your RC bond is formed, this bond, CC bond, is more stronger in comparison to CN bond. If CC bond is more stronger in comparison to CN bond, then alkyl group will prefer to connect itself with CN from carbon rather than from nitrogen. Again, I'm repeating it. Why alkyl group is specifically getting connected from carbon, not from nitrogen? The reason being CC bond. CC bond means carbon of alkyl group and carbon of cyanide. This is the stronger in comparison to CN bond. So it will prefer to make strong bond, and that could be made only by connecting with carbon. So it prefers to choose carbon instead of nitrogen. So 2 points, main things are coming. One is KCN is ionic. So CN is having the capability to get itself attached either from carbon and nitrogen. And secondly, why alkyl is choosing only carbon? Because CC bond is stronger than CN bond. I hope this explanation is well clear to you. If not, then you can ask me in your doubt session. Now moving forward, that why in the case of AgCN isocyanide is formed, not cyanide. Now if you see AgCN, the silver and cyanide is having covalent bonding, not ionic. And when covalent bond is there, the carbon of cyanide is already involved with silver. It is not having electrons available to give as a nucleophile, because already it is bonded to somebody, that is silver. So only nitrogen is left from where it can give electrons. So that is why only nitrogen is getting bonded to the alkyl group, because only this site is left, nitrogen. From this side, your carbon, it is engaged in covalent bonding with silver, so it can give its electron easily from the nitrogen side, because the job of the nucleophile is to give electrons, and it will prefer to attach itself easily from the side from where it can give easily those electrons, and that is the site of nitrogen. And why not carbon? Because from carbon the electrons are not available for give as a nucleophile, because it is involved in the covalent bond with silver, so they are not available to be given as a nucleophile, right? So that is why, so again here I'm talking about two reasons. One is the covalent bonding between AgCN, because of which the carbon is engaged in covalent bonding with silver and the electrons are not available to be given as a nucleophile. And secondly, your nitrogen is having the availability of electron to be given as an electrophile, so to be given as a nucleophile. That is why alkyl group will prefer to get itself attached from the side where the nitrogen can easily give the electrons. So this is how the product formation is getting affected in these cases, right? So I hope this explanation is clear to you. Now I'm switching to the next part of it. If I talk about this reaction, this is potassium nitrite. If you heat alkyl halide with potassium nitrite, you see, again here I will talk about the same thing. Potassium nitrite, here it is having ionic bond. So in that ionic bond, oxygen will be carrying negative charge, and negative charge means excess of electrons are available from the oxygen side. So it will get attached to this alkyl easily and resulting in the formation of RONO, that is alkyl nitrite. And if I talk about this in the case of silver, silver nitrite, here it is having a covalent bond. So in the covalent bond, the electrons of oxygen will be involved in the covalent bonding and will not be available to be given as a nucleophile. Means here your oxygen is involved in covalent bonding with silver. So it cannot give its electrons because its electrons will be involved in that covalent bonding. Now the electrons of nitrogen, this lone pair of electrons of nitrogen is easily available. So it will prefer to work like a nucleophile from here, from nitrogen. So here nitrogen will be bonded to this alkyl group and the product formed will be nitroalkane. Instead of alkyl nitrite, it will be nitroalkane. Nitroalkane. The same reaction I have explained to you here. Now, what about the preparation of alkyl iodide? If you see, if I take alkyl bromide or alkyl chloride and I react it with Ki, potassium iodide. Potassium iodide. Now, here I negative is a strong nucleophile. Will be displacing this one, bromide and chloride. In the presence of acetone, what is happening? Iodide will be displacing and forming alkyl iodide. This is again a very famous reaction, and this is known by the name Finkelstein reaction. I'm not written here. It is Finkelstein reaction. Finkelstein reaction. This reaction is specifically used for the preparation of alkyl iodide. Very famous reaction, Finkelstein reaction, used for the preparation of alkyl iodide. Thank you. My next topic will be on the mechanism of nucleophilic substitution reactions, which I'll be sharing with you soon. Thank you, students, and waiting for your doubts regarding these two classes. Thank you.